Hi everyone, I'm Jing-Jing Duflot. I'm the architect of the HPU project at Zama, where I've been working for 3 years now. And before that, I've been a hardware designer and manager. I got the opportunity to work on high-frequency designs, on designs where the latency matters, and also on systems where the quantity of data to process wasn't negligible, like in video decoding or also in video display. So today, I'll talk about the HPU. On FPGA, HPU stands for Homomorphic Processing Unit, is the very first open source processor for homomorphic encrypted data. I'll show you why it's a real processor. And you will see also that this project, the HPU project, is not a proof of concept. It's a complete industrial project, which includes an accelerator for TFHE, a hardware one, a complete software layer with an easy interface, and also a software ecosystem to develop the HPU code. So the project is open source, it's a premiere. It's now available on GitHub. You have the link just right here. And I encourage you to take a look, maybe just right now, but after the conference. So if you're ready, we can start. Oh, sorry. Oh yeah, it's working. So this first slide presents the interactions between an application and the HPU. So it's a very top level one. We can see the application as a set of operations on integers, any kind of operation and any size of integer. The application will send these integers and operations to the software layer of the HPU. This software layer is TFHE-RS. TFHE-RS is well known as a cryptographic library, but it's also an HPU backend now. We have implemented an HPU backend inside. So from the cryptographic part, what we will use is, for example, the encryption. We will encrypt the integers into ciphertext. We are using the same representation as in TFHE-RS, that means the radix2 representation. And the cryptographic part will also be in charge of generating the bootstrapping key and the key switching key. For the HPU backend, what does it do? It's in charge of formatting the data so that the HPU can work. So for example, it translates the user program into an HPU IOP program. IOP stands for integer operation. All these, so ciphertext and IOP program, are sent to the HPU. The HPU, the first thing it does is to convert this IOP program into a DIOP program. DIOP stands for digit operations. Actually, the HPU works on ciphertext, on elementary ciphertext. So it needs a program that concerns this ciphertext. That's why this conversion is necessary. The HPU executes this DIOP program, does some computations on the ciphertext, and once the result is available, it is sent back to TFHE-RS. Of course, the cryptographic library of TFHE-RS will decrypt the result, and it is sent back to the application as an integer. So from the application point of view, the interface is quite simple. It has not manipulated anything that is cryptographic. So as you can see, we have made things simple. So now let's take a look at the HPU and see what is inside. So here is a top-level schematic of the HPU. On the right, you've recognized the software stack with the application on top of it, TFHE-RS, the HPU backend. And since we have implemented our HPU on Xilinx FPGA, we are using an AMD Xilinx driver. This software talks to the HPU via a PCI Express link. There are two entry points, the large memory, where the ciphertext are stored, and the cryptographic keys. And the second entry point is the controller, where the IOP program is sent. Of course, we have implemented a key switch and a bootstrap. This is the key module of TFHE. Since we are using FHE on Taurus, we have programmable bootstrap. That means that we can apply any kind of function on the ciphertext, and this is done by using some lookup tables. So the LUT are stored here in the memory. Actually, what we did on the HPU is to build a processor around this key switch plus PBS. So finally, this function is only a processing element of our processor. For those who know the architecture of a processor, you will recognize a register file. We are using a register file of size 64, and here a register stores a ciphertext instead of an integer. So every elementary operation are done on ciphertext. You also recognize an arithmetic logic unit, which is in charge of all the linear operations like addition, subtraction, or even multiplication with a scalar. We have the processing element that is in charge of loading and storing the ciphertext from the memory to the register file. And the last part is the controller, who is in charge of the instructions. So an IOP program is sent from the software to the controller. This latter is in charge of translating it into a DIOP program. This is done in a very simple way by the controller. Each IOP has an identifier, and with this identifier, the controller is able to retrieve the corresponding DIOP code that is stored in the memory. Once this code is available inside the controller, the DIOP instructions are scheduled to the different processing elements. This is done with a look-ahead window of size 64. That means that the controller is able to look in the future up to 64 instructions in the future and to see which one are independent, and then it's able to schedule them on the different processing element. This way, we are using the HPU in an optimal way because we are using several processing elements in parallel. Now, let's take a look at these different programs. Now we have 3 programs. A user program is the one that is on the application, its translation into an IOP program here, and the DIOP program, which is the one that is executed on the HPU. Let's take a concrete example. Let's say that the application needs to compute the absolute value of A minus B. A way to write that would be, for example, first do a comparison. If A is bigger than B, then the result would be A minus B. On the contrary, the result would be B minus A. A translation of that in IOP program is first, we do a comparison, then 2 subtractions, and finally, a selection. Actually, here we need to do 2 subtractions because the result of the comparison is hidden. It's a ciphertext. So we can't skip a line of operation. One thing that is important here is, as you can see, the IOP program is completely readable. It's easy to read and you can understand it. Here, I've used the IOPs here that belong to our catalog. That means that they have already been defined by us and they have an associated DIOP program. If ever you need an IOP that is not in our catalog, it's very easy to define one. You only need to take an identifier that is free, and you have to define the associated DIOP program. In the project, we have developed some tools that help you to do that, so there is really no difficulty to do it. A second thing that is important here is that, for example, in this computation, we have intermediate results, the result of the comparison and the results of the subtractions. These intermediate results remain within the HPU. That means that the software does not need to retrieve them. So we have done a system where we are limiting the quantity of data movement from the HPU to the software. Now let's take a look at the DIOP program. For those who are familiar with it, my answer is yes, the DIOP program is an assembly code. You recognize it by its form. So we have a command, and the operands are either register, either a location in memory. For some command, we also have some extra information for them. So to convince you, you will see that we have, for example, the load command. loading from the memory into a register, the store command, storing from a register into the memory. We have some linear operation, addition, scalar subtraction, multiplication with an accumulator, And the new one is the PBS. It's not only the PBS, it's key switch plus PBS. So it's the processing element that I've presented earlier. The PBS works on a register to a register, and it needs a LUT. Here again, these LUTs are the ones that belong to our catalog. And if ever you need one that does not exist, you just need to define it. So it is as simple as that. If you know how to write an assembly code, and if you know a few rules about the usage of the PBS, you are able to write a DIOP program. Now, let's take a look at the HPU in action. So after the reset, the HPU needs to be configured and initialized. The initialization consists in loading the cryptographic keys, loading the lookup tables, and loading the DIOP code and their association to the IOP identifier. Now the HPU is ready to be used. First of all, we need to load the ciphertext. So in our case here, it's A and B. We need to load the IOP program. And now the HPU is totally autonomous to work. The controller will translate this IOP program into a DIOP program, and it will schedule all the DIOP instructions. Once the result is available in a register, it is stored back in the memory. The controller will notify the software that the result is available, and the software will be able to retrieve the result. As you can see, the quantity of interaction between the HPU and the software has been limited to a minimum. So it's quite simple again. Now let's take a look at the key switch plus PBS module. It's the biggest module of the HPU. But first of all, we will talk about cryptographic parameter set. I know this subject is not the funniest one, but it's an important one because this parameter set determines the architectural choices that we've made. So today, we are using a parameter set that satisfies a probability failure of 2 to the power minus 128, which is quite small, a security level of 132 bits, which is quite high. We are using a T-uniform distribution, and we have implemented the mean compensation into the hardware to satisfy this parameter set. So the main figures are the size of the polynomial, which is 2048 coefficients, and we are using coefficients of 64 bits. We have only one single mask polynomial, and we are doing 879 iterations of CMUX. One exotic parameter here is the size of the key switching key, which is 21 bits. This value has been verified by our optimizer, the lattice estimator, and a lot of noise measurements. This value is very handy for us. First of all, of course, it reduces the size of the key switching key, but it also reduces the size of the operators that we are using in the key switch. And you will see that this is quite important for us. Now let's jump inside the bootstrap. And one of the main elements of the bootstrap is the CMUX. Here is a translation of the CMUX operation with, well, hardware blocks. So you recognize here the loop that is necessary for chaining all the CMUXes that we need to do. On the right here, you will find the RAM that stores the results of each iteration and the accumulation here. And concerning the convolution, like everyone else, we are using an entity to reduce the quantity of multiplications to do. Of course, a multiplier is very costly. I'd like to introduce a notion that is very important for the HPU. This notion is the batch. So we have implemented the CMUX with a pipeline. And we can fill this pipeline with some ciphertext. And this set of ciphertext is processed from one iteration to another one. So this set of ciphertext forms the batch. Today in the HPU, a batch is composed of 12 ciphertexts. That means that we can do 12 PBSs in parallel. We can do more, of course, but it will take more time. And we can also do less, but actually it would take the same duration as the 12 PBSs. So the batch is the optimal number of PBS that we can do in our HPU. There are two entry points inside the CMUX. The first one is an entry from the key switch. What we've noticed is that the key switch does not need to compute all the coefficients of all the iterations of all the ciphertext. It only needs to compute the coefficients for the current ciphertext of the current batch and for the current iteration. That reduced a lot the number of coefficients. So we have built a key switch that is quite small, and more important, the thing is that we can make the key switch work in parallel of the CMUX. So here's an example. For example, if the CMUX is working on iteration I, the key switch can work on the coefficient for the next iteration, I plus 1. Then, once this is done, the CMUX can work on iteration I plus 1 because the coefficient will be ready, and the key switch will work on iteration I plus 2. Another entry point of the CMUX is the bootstrapping key. As we've seen together, the key is stored in the large memory. This memory can be a DDR or an HBM, and so the latency and the delivery pace of the coefficient of the key cannot be ensured, cannot be regular. And we need this regularity because we are able to process data at each cycle in our CMUX. That's why we have solved this by using a cache that can do prefetch. So we solve the latency with that, and with some local RAMs. And with that, we solve the fact that we can have a feeding of the key coefficient that is regular. We are using a cache that has 8 lines. Each line can contain a part of the key that corresponds to one iteration. Now, let's jump inside the entity, which is one of the biggest modules of the HPU. As said previously, we are working on coefficients of 64 bits. That's why for the entity, we've chosen a prime that has this form. It is the Goldilocks prime. This prime is very handy because it has a very easy modular reduction. The first property is due to the fact that this prime has a Solinas form, and the second property is due to the fact that the middle power here is half the value of the highest power here. So with these two properties, you see that we can do modular reduction without any multiplication and without any division neither. On top of that, the Goldilocks prime has also another very friendly property. It has friendly twiddles. So one of the 64th root of unity of this prime is 8. That means that for some size of radixes, we don't need any multipliers. For example, we can build a cyclic radix of size 64 without any multipliers. We can build a negacyclic radix of size 32 without any multipliers. So the size of our entity, looks like this. We are processing 128 coefficients in parallel. We start with the column of radix 32 of negacyclic entities. Then we go through a network. This is necessary because we work on polynomials of size 2048, which is not 128. So we need to reorganize the data to get a correct result. The same here. We need to multiply with some coefficients that correspond to an entity of size 2048 because we have not enough coefficient here in our local entity. This is the only place in our entity where we need some real multipliers. Then we end up with the radix cyclic of size 64. As said previously, the entity is one of the biggest modules of the HPU. That's why we worked a lot to reduce its area and resource utilization. So we've found that with partial reduction, that means that we don't do the modular reduction until the end. We stop at 66 bits. We are reducing the resource usage a lot of around 20%. So this is really not negligible. Now let's take a look at the results on an FPGA. On the right, you will recognize an FPGA. We are using the FPGA that is on the AMD Alveo V80 board. This FPGA has two HBM2E on the top in yellow, which is very handy because we need a quite high bandwidth for the key readings. It also has a network on chip in green here, also very handy to transport the key from the north to the south of the FPGA where it is used. Everything that is in vivid color is the key switch plus bootstrap. Well, actually that means that it's everything, almost everything. So I was not exaggerating when I said at the beginning that we built the HPU around the key switch plus PBS. It is exactly the case, as you can see here. Something that is interesting, well, for me, is the placement. Here in purple, you have the key switch. Here in magenta, the accumulator. In cyan, the entity. In light green, the multiplication with the bootstrapping key. And in orange, the identity. So you've recognized here the loop back that we are using in our CMAX. What we can observe also is that we are quite cramped in this FPGA. We are using a lot of it. For example, we are using more than 80% in these two SLRs. We are also using a lot of inter-SLR connectivity. So the lines that goes from one part of the FPGA to another part. And so that means that for future improvement, it will be less easy than at the beginning. But still, we still have a little bit of space there. Maybe we can implement other things. Now let's take a look at the performances. Here is a subset of the IOPS that are in our catalog. We intend to implement maybe not all, but most of the operations that are in TF-HRS. It's not the case right now, but we are catching up. So these results have been measured. So we did the measurement inside the software layer here. So just after the encryption and just before the decryption, we are using an HPU that is running at 380 megahertz. That makes that the PBS batch latency is around 950 microseconds, so a little bit less than 1 millisecond. And I am quite proud to say that today with this elementary operation, even for 64 bits, everything is in millisecond unit, which wasn't the case a few times ago. I can take a simple example. The multiplication is now at 137 milliseconds for multiplication in 64 bits. This is quite fast. This makes the multiplication usable for some application. Don't forget that the HPU is a processor. It has a program, so the DIOP program. We did some profiling on these DIOP programs. What we've noticed is that there are two behaviors that are important. The first one on the left is a program where the PBSs are dependent. So we cannot do one PBS before finishing the previous one. In this case, a system is optimal if the latency of the PBS is very short. In the second case, on the right, we have observed programs where we have a lot of independent PBSs. In this case, for a system to be optimal, we need actually a lot of throughput. That means that we need to process a lot of PBSs in parallel. In the HPU, we have a very short latency for the PBS, which is less than 1 millisecond today, but our batch is not that big because we can process only 12 PBSs in parallel. So our next move will be to improve our DIOP code to make it more suitable for our HPU architecture. We can, for example, improve the scheduling of the DIOP instructions. We can choose a different high-level operation algorithm for the high-level operation. We can also customize the DIOP program for the application. For example, if an application needs some throughput for a single operation, we can write the DIOP program as a SIMD. That means single instruction, multiple data to improve the throughput. Today, we are also working on a system that supports multi-HPU. So to have a software that can handle several HPU. This is useful, for example, if you need throughput, but this is also useful when you need something that it has a low latency. For example, we can cut the DIOP code into several parts, and these parts are executed on different HPU in parallel. And so, since they are running in parallel, we can reduce the latency of the operation. So, as you can see, we still have work to do on the hardware side, on the DIOP code side, and also on the tools, because they are important for our development. So, as a conclusion, I would say that the HPU project is a whole system. It's not only an efficient PBS, but it's also some hardware and software that makes it a real processor, optimized and easy to use. The whole ecosystem of tools that we have developed makes the development of IOP and DIOP very accessible. So again, the HPU project is open source. So don't hesitate to take a look. We are sharing our progress quarterly. And if you don't have an FPGA, this is not a problem, because we have developed a mockup which is able to emulate the behavior of the HPU, so the FPGA. So all you need to do now is to give it a try. So thank you very much for your attention. And if I wasn't too talkative, we have a few minutes for the questions.
Yeah, thank you very much, Jing-Jing. That was great. So there's already 3 questions in the chat, so I think we have time for all of those. The first one is from Sheriff. Where do you store your twiddle factors for NTT?
So for the radices, where we don't need any multiplications, the twiddles are constants, so we don't need to store them. And concerning the phi column, the multiplication by phi, actually there are not a lot of them, so they are only constants, so we don't really need to store them. We can write them like that in the code. And so we don't need ROM, we don't need RAMs. They are only constant, and we select them according to the iteration of the computation we are processing.
Okay. The next one, we have a question about the key switching modulus. So the question is, are you running the key switch on 32 bits?
We are, oh, sorry. Could you repeat the question, Ben?
Yeah, so it's just about the key switching key modulus, I guess. And it's,
yes.
Are you running the key switch on 32 bits with a 32-bit modulus, I guess?
So we are running it on 21 bits because we are using a key switching key of 21 bits.
Okay, and then from Mutu, we have a comment. The HPU can become a target for the Hare compiler project for CGGI and TF-HRS Stylex. Yeah, I don't know if you want to say anything about that, Jing-Jing.
Sorry, I'm not very aware of that, so I don't want to say anything silly.
Sure, no, that's okay. We have the that's actually going to be spoken about in the next talk, so we can forward it on to the next speakers. Okay. And the last question is about Concrete ML. So does it support Concrete ML?
No, Concrete ML is a complete different project.
Okay.
Yeah.
Great. Well, that's all the questions. So Jing-Jing, thank you again very much.
Thank you very much.
Taking the time, and it was a great talk.